working in Kungrad College of Engineering Technology. So in this college located in the Totium. Today we are saying the thermal engineering one subject under University 2017 regulation. So today we are discuss about the topic is Brayton cycle problem. Okay. So this is the problem. So first we taking the given data. So in a Brayton cycle, the air enters the compressor 1 bar. So the air is entering the compressor at the state of 1 bar and 25 degrees Celsius. The pressure of air leaving the compressor is a P2 value 3 bar, and the temperature at the turbine inlet is 650 degrees Celsius. So entering your turbine after combustion process, the temperature will be increased. That is the peak temperature, that is the T3, 650 degrees Celsius. So determine per kg of air. First one, the cycle efficiency, then heat supplied to air. Third one, work input. Fourth one, heat rejected in the coolant. Fifth one, temperature of air leaving the turbine. So these are the values we have to determine from this problem. Okay. So first we write the given data. So P1 and T1, P2 and T3 is given our problem. Okay. So this is the PV and TS diagram. So here we are saying two constant pressure cycle, another two isothermal process. So this is 1 to 2 is the isotropic compression process. So this is a compressor working into the 1 to 2 process. So gradually the pressure will be increased, so 1 bar to 3 bar. So the directionally proportional to the pressure and temperature. So 1 to 2 process, the temperature also increased. Okay, that shows the T1 temperature 25 degrees Celsius. So here T3 temperature is 650 degrees Celsius. So 2 to 3 process is the combustion process. So in the combustion process we are giving the heat from the combustion chamber. Okay. So after the leaving the combustion chamber, it is the hot air entering to the turbine. So then the turbine process is the 3 to 4 process. There is the expansion process. Okay. So this is the 1 to 2 process. This is the finishing of our cycle. So then we are going to find the temperatures T1 and T4. Okay. So we are considering the 1 to 2 process. This is the adiabatic compression. So this is we are taking the thermodynamic process. So temperature relation and pressure, it is a T2 divided by T1 equal to P2 divided by P1 power of gamma minus 1 divided by gamma. Okay. So pressure and temperature relation using, we are finding the value T2. Okay. Already we know that given for the P2 and P1. Okay. So multiplying to the your T1 temperature. So finally we can get the T2 temperature 407.88 Kelvin. Next we are going to find the value of T4. That is consider the process 3 to 4 is the adiabatic expansion process. Okay. So we are another relation is, that is the temperature and the pressure relation. Okay. So 3 to 4 process. So we are considering the adiabatic expansion. So we are taking the temperature T4 divided by T3 equal to P4 divided by P3. Okay. So power of gamma minus 1 divided by gamma value. Okay. So we have to know find the T4 temperature, then only we are taking the T4 in left side. Okay. So T4 equal to P4 divided by P3 power of gamma minus 1 divided by gamma into T3. Okay, so we know that P4 temperature, that is a P1 temperature, that is equal to P4 temperature. Sorry, the pressure is constant. P1 equal to P4. So P1, the P4 pressure is 1 bar. Okay, divided by P3 value is 3 power of gamma value 1.4 minus 1 divided by gamma value is the 1.4 multiplying to the temperature T3. Okay, 923. So here getting the T4 temperature 674.34 Kelvin. So then we are going to find the air standard efficiency. There is a formula is 1 minus 1 divided by pressure ratio power of gamma minus 1 divided by gamma. Okay, so there we know that pressure ratio 1 to 3 1 pressure 1 bar pressure to 3 bar pressure. So this the pressure ratio is 3. Okay, so power of gamma value 1.4 minus 1 divided by gamma value 1.4. Okay, so where from the value is, finally we can get the air standard efficiency 26.94 percentage. So next we are going to solve the heat supplied and the heat rejected. So heat supplied is the process, so 2 to 3 process. Heat rejection process 1 to 4 to 1 process. Okay, so our heat transfer formula is general formula mcp into change in temperature. Here there is no mass value is not given, so that is cp into T3 minus T2. Okay, the cp value is 1.005 into temperature T3 minus T2. Okay, so heat supplied value is 517.7 kilojoule per kilogram. So next we are going to solve the QR, there is a heat rejected. Okay, so T4, here the temperature only we are changed. There is a change in temperature, there is a heat rejection process 1 to 4 process, so T4 minus T1. Okay, so already know that where all the temperatures, so finally we can get their heat rejection values 378.22 kilojoule per kilogram. Okay, next we are going to solve the compressor work. So compressor work is the 1 to 2 process. Okay, isentropic compression process. So cp into change in temperature. Suppose the temperature we are taking the T2 minus T1 into cp value, so we can get the work done of compressor 110.43 kilojoule. Next we are going to find the value of turbine work. So turbine work is the 3 to 4 process. Okay, so is the isentropic expansion process. Okay, so T3 minus T4 multiply to the cp value, so our turbine work is 249.9 kilojoule. Okay, next work where we can find the value is work output W, this is equal to work done of turbine minus work done of compressor. So already we are finding already we are calculated the two values, compressor work and turbine work. So this value subtracting another, we can finding we are getting the value is 139.47 kilojoule per kilogram. So this is the work done of our output. Okay, next value is the temperature air leaving the air leaving the turbine. After turbine, the what is the temperature? This question will be asked in our problem. Already we are find out the values T4. The T4 is the leaving temperature our turbine. After the turbine, this is the T4 temperature is 674.34 Kelvin. So this is the finishing our problem. Thank you for watching. Thank you.